All right, so we're going to do a couple of examples from worksheet 5. We're going to do problem 1 together first. And there's just not a lot of room on that worksheet, so that's why I'm working off just a plain document. I want you to notice that on worksheet number 5, questions 1, 2, and 3 ask you to work them by both methods. So we're going to actually do problem 1 and 2 together, and that should be good enough for you guys to be successful on 3. And then we'll choose a couple other problems from the remaining problems. Okay, what we've been given is a rate, a derivative. We've also given a value on the antiderivative at x equals 1. And we're asked to find a y value on the antiderivative of y prime at 3. So what do they mean by both methods? Well, let's start with the first method. Something that we've done in the past. When we first started our study of integration, we performed anti-differentiation. So that's what I'm attempting to write right here, anti-differentiation. The pen's acting kind of funny, so hopefully it'll go okay. Well, anti-differentiation just means find an antiderivative, and what we did was we put on a constant of integration. Before we had the FTC constant here, okay, we found an antiderivative, we added the plus c, okay, and what we could do then is, with this method, is we could evaluate the antiderivative at x equals 3. Oh, this pen. So this is our input at x equals 3. So let's see what that looks like. All right, so what we did was we looked at y prime. Now I could rewrite that as dy over dx. I could keep it as y prime. I'm going to go ahead and write it as dy over dx. What we did was we pulled over the dx. We got rid of this rate expression, so to speak. If you remember, we pulled over the dx. We separated our variables. Put the x's on one side of the equation. Oh. All right, then we brought in the integral symbol. Then we found the antiderivative of 1, which was y. We're going to put the plus c over here. Notice I have an indefinite integral, indefinite, no limits. The antiderivative for 2 is 2x. Reverse power rule on this term. Well, I'm going to increase the exponent by 1 to negative 1. I'm going to divide by negative 1, but dividing by negative 1 would just change the plus to a minus. Then we added the constant of integration. So this is the antiderivative. Okay, now to find c, we use this initial condition. So I'm going to plug 6 in for my y. Remember, this is x and this is your y value. And then 2 times 1 minus, this is just 1 over x. So that would just be 1 over x is going to be 1 here plus c. So let's find c. So 2 minus 1 is 1. Subtract from 6. 5 is c. Oh. Okay, so what I'm going to do is come back up here and I'm going to rewrite y with the constant of integration. So 2x minus, I'm going to go ahead and rewrite it as 1 over x plus 5. Maybe. Okay. All right, so at this point, remember what we're asked to find. We're asked to find y of 3. So we found an antiderivative by using the constant of integration. We found that. Now let's evaluate our regular function at 3. So what's y of 3? Well, 2 times 3 is 6 minus a third plus 5. So that's 11 minus a third. So 11 minus a third is 10 2/3. So that's the answer, 10 2/3, by using this technique. Okay, I'm going to change colors. Maybe that's going to stop the pen from acting crazy. We'll see. All right, so my second method is to use the FTC. Well, looking at worksheet 3, okay, that's not helping. Looking at the worksheet 3 that we just looked at in the earlier video, okay, the second method, the FTC, is to use the fundamental theorem of calculus. Well, here's the generic format. No. So we know the change here is equal to the difference of the two y's on the antiderivative. So f of b minus f of a. And what we're going to do is we're going to customize this for my problem. So for here, what we're doing for problem number 1 is my limits go from 1 to 3, my input values, so 1 to 3. Their notation is y prime, and it's in terms of x. So we've got an x here. So what does that look like customized over here? Well, the antiderivative for y prime would probably just be y, evaluated at the upper limit of 3. So f evaluated at the upper limit of b here. So y of 3 minus y of 1. Okay, the color change didn't help, I see. Okay, so continuing then here, what I want to do is I want to find y of 3. So I notice that y of 3 is here. I'm going to add y of 1 to the other side. And then I'm going to trade sides. So, oops. So y of 3 is equal to y of 1, which means the y value here, oops, plus, not good. So it's going to be y of 1 plus the integral from 1 to 3 of y prime d of x. So I think you see where this is going. I'm so sorry. I don't know how to fix this situation with this pen. All right. So in this case, let's find y of 3. I strongly recommend you guys to pull down y of 1 and not put 6 in just yet. Okay, so it's y of 1 plus, so we have some work to do here. All right, well, what's y prime? Well, y prime was what we had here, the function. Okay, I'm going to add to this. Now, we're going to have to do the antiderivative here. We've already done it over here, so I'm just going to steal it. This should have been a dx here. So the antiderivative is 2x minus, 1 over x. Now, remember, with the fundamental theorem of calculus, we don't have a plus c because we have limits. We have a definite integral, so we put the 1 and the 3 down here. So next line down. I'm still going to bring down y of 1. I'm just afraid if I bring down 6 here that I'm going to try and evaluate, and not that it would be wrong or anything, but I'm just going to leave y of 1 here. So plus, okay, so I'm going to evaluate the antiderivative at both 3 and 1. So I'm going to kind of get myself set up here and say, you know what? Everywhere I see x, plug in 3. So that would be 6. 2 times 3 is 6. 6 minus a third. And in the FTC, it's minus the antiderivative evaluated at the lower limit, so that'd be 2 minus 1. And we just have a little replacement to do and clean up here. So y of 1 is 6 plus, this is just 1. So 6 minus 1 is 5. So this becomes what, 5 minus a third? Don't really need the parentheses. So in this case, that's 11 minus a third, which is the same thing I found over here in the alternate method. So we knew we should get the same answer no matter what method. So y of 3 equals 10 and 2/3. So we've got the same answer 2 different ways. Okay, so both methods on this one as well. Okay, so for the first method, it's anti-differentiation. Find the constant of integration and then evaluate the function you find at pi over 4. So I'm just going to go ahead and get started with the problem. Okay, so I know that I've got to integrate f prime of x and integrate cosine of 2x. Just remember, we're going to go ahead and include the symbol dx. So we'll just bring in an integral symbol on both sides of the equation along with the differential. Okay, integrating this side of the equation, we lose the rate and we get back to f of x. Okay, over here, if we've done u substitution, this would be the place where you'd want to use u substitution. If we haven't done u substitution, we can reason through and find the antiderivative mentally. We know cosine is the derivative of sine, so my antiderivative is going to be sine of 2x. If you were to, and I'm going to put a plus c here, if you were to check and differentiate sine's derivative of 2x, if I were to find the derivative of sine, I would get cosine, I'd leave 2x alone, but in the process of differentiation, I would have to multiply by the derivative of the inside 2. Well, there's not a 2 here. So how would I get rid of that 2? Well, okay, by the process of differentiation, introducing that multiplication by 2 could be undone by multiplying by half. We haven't done u substitution. We're doing this mentally. If we have done u substitution, then we would know why the 1/2 has to go there. All right, now let's go ahead and use our initial condition to find c. So I'll replace f of x with 3 because I'm replacing x with 0. So remember, this is 2 times 0 first. Multiply 0 times 2. So sine of 0 is 0. 0 times 1/2 is 0. So it looks like c is just 3. So rewriting the function, I'm going to have 1/2 sine 2x plus 3. Okay, now to find the answer, the function evaluated at pi over 4, I'm just going to insert pi over 4 everywhere I see x. So remember, we're going to multiply 2 times pi over 4 first. I knew that was going to happen. So, yeah. Sine of pi over 2 is 1. 1 times 1/2 is 1/2. 1/2 plus 3 is 3.5. Second method is the FTC. All right, so let's think about what we have here and what we're finding. We're finding a y value at pi over 4, which this input pi over 4 is larger than the input of 0. So using on worksheet 3 one of the alternate forms of the FTC, I'm going to just go ahead and go right to the setup. Using the second method, f of pi over 4 would be equal to the function evaluated at 0 plus any change that occurs from 0 to pi over 4. Think of this as your b, your a, your b, your a, on the derivative f prime of x dx. All right, so let's just go ahead and do the setup here. Again, as suggested in the earlier example, I'm just going to leave this as f of 0 until quite near the end. I'm so sorry. I don't have an answer for why this pen is doing this. All right, the antiderivative, we already found it. It's 1/2. Remember, we don't need a plus c because we have a definite integral. So in this method, we would use the FTC. Oh my gosh. Okay, and I might suggest, because I have a constant multiplier, I might suggest leaving the 1/2 out in front, just to kind of, simplify your numbers a little bit. So I'm going to evaluate this variable part at pi over 4 and at 0. So it's going to be sine of 2 times pi over 4, or sine of pi over 2. And then I'm going to insert 0, so then it's going to be sine of 0 in here. And if I can get through these calculations without too much disappearing, hopefully we'll see we have the same answer. F of 0 was 3. We're going to add that to 1/2 of whatever I get within the brackets. I'm sorry. This probably was sine of pi over 2. Twice pi over 4 is pi over 2. So that's 1 minus 0 within the bracket. So 1 minus 0 is just 1, 1/2 of 1. It's funny how sometimes it comes back. So after it's all said and done, hopefully it's not disappearing on your own paper. We get 3.5. All right, use the FTC. It doesn't give us a choice, or it doesn't tell us to use both methods. So let's take a look at how we'd set that up using the FTC. All right, our input values are 2 and 5. So those become our limits. So we're going to integrate f prime of x. I'm doing a setup of the fundamental theorem. All right, so what does that look like in notation? Well, that means that f evaluated at 5 minus f evaluated at 2, okay, would be equal to the value of this integral. Okay, so now let's customize it. Well, what I'm finding is f of 2. So f of 2, and notice what we're finding. We're finding what the value was at an earlier time at 2 as opposed to 5. So I can move this over here. I would leave f of 5 on the right-hand side of the equation, but I'm going to subtract the value of the integral from 2 to 5. Okay, so this is an interesting situation right here. So just wanted to point out what's interesting is I'm finding an earlier y value, or an earlier x, if you will. 2 is less than 5. So instead of adding, okay, we're going to subtract. So it's important to pay attention to what you're finding. Okay, instead of adding, we're going to end up subtracting. That's the alternate form. All right, so how do we go about finding this answer? Well, it said use a calculator. F of 5 will be replaced with 1. Go right to your calculator. Remember, that's the derivative. Type in the function to y1 using the appropriate keystroke. Find this value. And when I did that, I got 0.004145. And when I subtracted, I got 0.99585 to 5 decimals. So easy enough. What they're looking for is, do you know how to set up the FTC on this problem? Okay. And the point really here is this. I can't find this antiderivative. I can't find it unless I have a calculator. I can't find it by hand. Okay. All right, to continue our work, if you look at the next group of problems, it's 11 through 13, meaning that's where the directions change. So it says use the FTC in the given graph. So let's just take a peek in at number 12. Okay, it tells us that the graph of the derivative is shown at the right, and it is a semicircle. So that's important for us. I'm doing some calculations. So trying to recreate the graph real quick. Looks something like this. Okay, so we're doing number 12. So this is f prime. All right, so it asks us to find the functional value at -4. Find f at -4, given that f of 4 is 7. Okay, you can use the fundamental theorem of calculus and then the graph to help us here. I'm gonna give it a second. It might show back up. Not this time. Okay, so if I'm finding f at -4, I'm finding a y value at a earlier time, if you will, or value. That means this number is smaller than this number. So that means a subtraction. So f evaluated at -4 is equal to f evaluated at 4 minus the change that occurred from -4 to 4 on f prime of x. So if we think about how to solve this problem, okay, we know the value at 4, easy enough. Later, we're going to replace it with 7 here. Okay, and then I'm going to subtract, okay, what I get from this integral right here. Remember, that's a prime, and that was an x and a dx. Oh, this is bad. Really, really bad. Okay, well, how do I find this? Well, it's a semicircle. So use the area formula for a circle, half it based on the radius that you see here. It looks like it's 4. And so once you find the value of that semicircle, you can take 7 and subtract 7 by that number. So it's just so bad right now. I'm just going to leave it, and hopefully you guys understand the setup here is to take 7, subtract the value of the integral, which you'd find by using the area formula for a circle. Okay, so just a little example of the different types of problems that you might be asked to do using the FTC.